Okay, we'll start in a few minutes, maybe 5 minutes. Okay. Mm, So, okay, everyone. So, we are going to get started on week 8. Okay, so we'll go to the lecture materials first just to have comprehension on what to expect in this week's question. Okay, so there's a video as well. I don't know if there is something useful there. Let's play that first. So you've read transformers, right? So what happens in RNN that you process the tokens one after another. Okay, there is sequential processing, but in a transformer, what happens that you serialize them or parallelize them. Okay, so in parallelize, when you parallelize and so you can process each of them parallelly. Okay, so that improves the computation speed. Okay, so you can also process larger sequences. So the video is not too good, but you can still see that. So here you can see that there are two languages. So and what are we going to show? So so here I'm not able to show that there are actually okay. So there are two languages. So this is Spanish maybe, and other the output is English. Okay, so so first you make an embedding out of it. Okay, and so with embedding in time signals they are doing. Okay, so the position encoding works. Okay, so that is the time signal here, I think. So then they transfer it to the encoder. Okay, and encoders. So in transformer there are K, Q, V actually. Three matrices are there, K, Q, V, which are all the same. Okay, so you then transfer the query matrix to the decoder. Okay, and then you get the softmax outputs. Okay, and whichever the output is bigger is has the highest probability of occurrence. Okay, so you predict that. Okay, so this is it. This is like the short video. Video wasn't too good, but still got into it. Now let's start with the lectures. Okay, and let's download this one. Am I audible? Am I audible? Anybody can respond? Audible and can see the screen? Okay, okay, okay. Very less representation today. So, so let us get started here. So RNN and everything is there, you know RNN, okay. Image captioning is one of the work of RNN, okay. And the corresponding work in case of natural language is machine translation. Okay, so this is like the multimodal input is there, okay. Image, video, audio, text, and everything, and the output text you get, okay. This captioning they are showing, so it's not too important here, okay. So they have moved to auto encoders, okay, and so usually in auto encoders the loss function is mean square, and in so auto encoders are like the encoded decoder network, okay, and so that is what you can see. So this is the code, or you can say the compressed representation, okay. Uh, Let me. It's compressed representation, okay, and so this denoising autoencoder is subtype here, okay. So where input is perturbed with noise, so that you add some small noise into it, so Gaussian noise, but network is asked to predict output signal without noise. So that makes the network more robust, okay. So that is it, you know, not very. Okay, so as you can see, uh, another another type of autoencoders which you must know is variational autoencoders, okay. And let me give you a so I've made a presentation on that, but it's currently not on these devices, okay. So I will just give me 2 minutes, and I will give produce the presentation here, okay. And so variation encoder is very important, so we're going to look at that. Just wait 2 minutes. So so let me get that presentation. And we'll skip for now. Okay. Okay, so this is the presentation on variation autoencoders. It is special type of autoencoders which is like the one of the best in autoencoders these days. Okay, and so it is called variational because we take a variational approximation for simplifying the loss function so that the loss function is optimizable at scale. Okay, so that is what we do here. So here what we do is like the data here. Okay, so here so as you can see this is the oh, so here this is the image. uh, so this is the image here. Okay, or data, any type of data. Okay, and you feed it to the encoder model which is usually a neural network. Okay, and the output of the model is mu and sigma. So what are these mu and sigma? Mean and variance. Okay, or standard deviation, what you say. Okay, so you using that. So from here what we are doing is we are sampling from a 0 1 normal distribution. Okay, so epsilon is sampled from 0 1 normal distribution, and you do this. Okay, so this linear combination results in normal distribution having mean mu, and variance sigma square. Okay, that is what you get. Okay, so this so z is sampled from this, like this. Okay, and then you feed this z into the decoder network and you get the reconstructed x. Okay, so this is the input x, this is the reconstructed x. We use a L2 loss in between them, or square error loss. This results and then minimize the loss. Okay, and this so using this you can train the model. Okay, so see if things get hard here, means so you may miss this. Okay, this is not like exactly in the syllabus. Okay, but it is the in autoencoders the most important autoencoder is variation autoencoder. Okay, so so continuing, so this px so what we need to learn in any autoencoder is the input distribution. So input distribution is px. Okay, we need to learn that, and it can be written as p x comma z dz integration. So when you integrate it, you get px, right? This is the sum rule of probability. So you are integrating this z uh, des z variable out. Okay, so it is removed from the, then you get the px. This is sum rule of probability. Okay, so so using this the rule of joint probability, you can write that px given z and pz dz integration. Okay, so that is what they have written. Okay, now this integration is often interactable. Okay, because we are integrating with respect to z, and z is of significant dimension. Okay, so 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 and so with each what do you say, each dimension of z, means z1 z2 z3 zn, if n is the dimension of z, you are integrating this. Okay, so there will be n integration actually. Okay, so that is why it is interactable, hence it needs approximation. Okay, so this is not possible to compute. Okay, and and approximation is required, that will be the variational approximation. Okay, so variational autoencoders is for used for various tasks. Okay, so first is anomaly detection. Okay, if you can know this px distribution, any image or any data which does not lie in the px distribution is an anomaly, and as the model, as the variation or autoencoder has learned that distribution, it can point out whether the given x is part of the px distribution or not. Okay, so after training the variation autoencoder, you can do anomaly detection. Okay, anomaly detection means whether it's part of the distribution or not. Fill in missing parts of an image in painting. Okay, so as you can see, in painting, suppose this is the image, small part is removed. Okay, you don't know, and you can fill that part. If you know the z, okay, then you can generate x. Okay, so this is the generation part, so you can do in image in painting. Okay, so remove noise or super resolve low quality images. Okay, so the thing is that you can super resolve low quality images. What does it mean? So you can understand that so the noise will not be part of the distribution, right? So so when you feed the image, okay, there, then what will happen, that it will means that it will not be able to learn the noise part. Okay, so it takes only the image part, and the reconstructed image that it gets, okay, will be the denoised image. Okay, so that is helpful in that as well. Now this is the Bayes theorem. Okay, and this is the posterior. Okay, and this is the likelihood, this is prior, and this is evidence. Okay, this is how it's called. So this posterior z given x is interactable. Okay, so now for learning px, you need to have this distribution p theta z given x. Okay, and but for that you need this px. Okay, and that is interactable. Okay, so it is not possible for now. Okay, now if you are able to so if you can get z here, then you can using this z, you can, and this decoder, you can generate the x values. Okay, so this generation problem can be tackled, but because this is interactable, this is not possible to calculate. Okay, any doubt up to this? I'm motivating the problem for now. Any doubt? Anybody understood the things? Anything anybody want to say? is this conditional probability. Uh, so so whenever the probability is written in this style, p x given z, it is conditional. Okay? Conditioned on z here. Okay, this is conditioned on x here. Okay, so this is called posterior. Okay. 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 Hmm. So this is it really. So this is the problem statement. The solution is detailed in the paper. Okay. We'll not go to the details of it here. Okay. And okay. So moving on. So so what they do, they consider n IID samples. There are n samples, and all of them are IID. Some continuous, some discrete variable. Maybe continuous, maybe discrete variable x. Okay. So first, the z is generated. So what we do that, we use a q phi z given x. Okay, this is the approximation. This will result into the variation approximation. So in place of p theta z given x, we will not which we were not able to calculate, we introduce this model. Okay, which is parameterized on phi. Okay. So after that you have two parameters, phi and theta, not single parameter theta. So theta is now the parameter only of the decoder. So as you can see, it has parameter phi, it has parameter theta. There are two models of different parameters. Now, so as these are IID, you can write it like this in summation form, and this can be resolved into this KL divergence form. Okay, and this is called the variational lower bound or elbow. Okay, elbow you can write it like this, and there, this is the loss function now. Okay, so okay, and this is called the reparameterization. Okay, and because like we sample z, the process will become non-differentiable. Okay, so they sample epsilon and make this is a deterministic function, which is explained here, and so that is why it is differentiable and it is done. It is possible to do it. Okay, so reparameter is explained here as well. So for details you can go into the paper, but I briefed it. Okay, it is the most important encoder structure. Okay. Okay, so we'll move on from now. Just to show you this, this is variation autoencoder. So this is the paper here. Okay, so by Derek P. Kingma and Max Welling. Okay, so everything is here. Another for more details into this, there is a uh, is another review paper. Okay, so this can be helpful as well. Okay, so the derivations are detailed here and the intuition as well. Okay, I will upload it. Okay, in this week's that note section. Okay, okay, so this is it. So you can find the detailed derivation there. Now coming to our point here. So this is the denoising autoencoder. So you can see more on autoencoders. So, so one solution of the denoising autoencoder is the result of a principal component analysis. Okay, so that part is there. So now, so these are the sequence to sequence modeling. Okay, so means the this is the translation problem. Okay, machine translation. So as you can see, so you're feeding data in English and you're getting data in Hindi sentence. Okay, so this also happens. Okay, and you can use both RN and transformer. Transformers are better because they are parallelizable. Okay, to get to it. If you don't know transformer, that's okay. So this is an image captioning problem here. So the image here is you feed it to a CNN, then the embeddings of the CNN are passed to a fully connected network, and the output that you get, the vector that you get is the context vector. Okay. Now you feed the context vector. So this is the X for this is series of RNNs. Okay, and then you can generate. These are all the YTs. This is Y0, Y1, dot 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 Yn. You can generate this. Okay, and out here, this is one to many problem. Okay, any doubt? Any doubt here? No doubt? Okay. So we'll move on here. So one too many problem here. So in sequential processing, another problem happens. So first thing is that you cannot process them all at once. Okay, that is faster method. Another problem is that the context vector, as the sentence length gets big, it keeps forgetting. Okay, so LSTM and GRE was a solution, but transformers are better. Okay, because it remembers everything actually. There is no forgetting here with transformer. So we focus on attention here, and the intuition is built first, and then we get to the mathematical rigor of it. Okay. So this is the image captioning problem. What is the boy doing? You can give an answer. Okay. And there is the text summarization, which is a task. Okay. So you can see uh, so this is the x inputs here, okay, and then you get to this. So hidden state h1 to ht in the encoder, and s1 to sk in the decoder, okay. So there's a context vector, keeping context of every h here, okay. That is important. So this context vector actually takes all the keeps all the hidden states, okay. And so you can see for the input there are this alpha alignment weight are there, okay, which with respect to every input hidden states, okay. So for every h1 there is a alpha for every h, okay. And you can see for every yt for a specific time that this y will be generated, okay. So you have different attention, different alignment weights, different context vector ct, okay, depends on the t, right. So that is what is shown as well, okay. The ct is defined as a linear combination of this alignment weight and embeddings, okay. uh, so that is ct. And now how do we get the alignment weights here? So they have a score based method, okay. So this is usually a neural network, in a small neural network, say mlp, and so it is fed st minus 1 and hj, okay. So what is st minus 1? The output embedding till yt minus 1, okay, and hj, okay. So up to hj is like uh, at that point, okay, and yt minus 1 is right before that, okay. So you feed this is like the softmax score, as you can see. So this is the one, and divided by what you get, j dash from 1 to t, okay. So what they're doing is that, so first what you need, for this you need to find the alignment score, right. So they get this exponential value and divided by, for every each of them they do it, okay. And this ratio is the, okay, so this ratio is the alignment weights, okay. So there are different types of attention here: content based attention, additive attention, dot product attention, okay. So the scores are different in each respect, okay. You can see that as well. Dot product, scale dot product, general attention, location based attention, everything is there. Now you're using not in language data but spatial data like image, okay. And this CNN encoder FC network S0 output offers no spatial information, okay. So so what happens is that when you're feeding the full image into it, it will give you a compressed representation, but how the objects are spaced around each other, okay, in the image, that information is lost, okay. Okay, Aya, what is your doubt? IR in the diagram. In the diagram, what? Above question. Where is the question? Can you unmute yourself? Otherwise, it will take too long. In the diagram above question. Not able to understand what you're saying. Can you unmute yourself? Sorry for the delay. The question is above in chat. Acha. Acha. Is T the number of samples or time step? How is T decided? So it is the time step actually, and time, and it is decided on like. Uh, so I am Anirban. Okay, so I'm going to write that I am Anirban. Right. So I comes at time t equals to 0. This comes at 1. This comes at 2. This comes at 3. So it is that only. What comes in another sequentially? What is the time of occurrence? Okay. So it is not like the time that clock time, but it is like one after another. That's it. Okay. So this is giving some special information. Okay. And it's projected back into the image, and so what they do, they take the embedding from the CNN, okay, or the hidden representation from CNN, and then feed into this whatever that is, MXNCX, NXC. I'm not sure what is MXN and NXC. Don't know what it is. There's no description here. Whatever that is, I don't know. Cannot find in the Google as well. So better we skip this one, okay? So byproduct of, so attention, with the attention you can have explainability. Okay, that's a very important concept here. So with this what you can see, so English to French translation, with attention you can see which word attend to each another word. Okay, so this L you can see attends to some the here and some signed here. Okay, accord here, it's, attend means, so when you need to generate, suppose accord here, acha, yeah. So this is the input sentence here, and you need to generate accord. Okay. So this is y1. This is y0. This is y1. Okay. So we'll get the context for c1. Okay. So this is the attention score. Okay. And they have different alignments here. So alpha 1 1, alpha 1 0, alpha 1 1, alpha 1 2, dot dot dot. The length of the English sentence. Okay. 1k. Let's say. So you can see that this alpha 10 is like a higher value in the softmax course. Okay, and this sign, so which is maybe like alpha 1m, is of higher value. Okay, so that is valuable to us. Okay, so similarly you can see accord agrees, goes to the agreement. So the sir goes to on. Okay, like that. La goes to the, and area, like that. So and so it learns through training, through iteration, and it is learned to give the appropriate attention score to which um, to which we get the most information. Okay, so that way it is able to do the okay. Here as well, the brighter place is mm, the brighter place gives the attention where it is attending actually. So if the brighter place is at the child, then it is giving some A. So I'm not sure what it means. If it is on the if it increases on the woman, then it feeds woman. Acha, acha. No, no, no. It is something else. So this is, I think, the image captioning problem here. So they feed the image here, and what should be the caption? Okay, and these are so the output is a woman is throwing a frisbee in a park. Okay, so now they're comparing which part of the image. Okay, now now they're comparing like the output that you get for each word, which part of the image it attends to. So A for A, not so clear. Okay, like, but a woman, here the attention improves. Okay, is still it is like confused. Focus on the woman and child both. Throwing, now this gets brighter, as you can see. A frisbee, so you can see focus shifts to frisbee here. Okay, now the park, then the whole picture gets highlighted except the woman and the child, like that. Okay, so you can understand somewhat. So usually it is soft attention only, so no, we're not going to details into that. Global versus local attention. So this self attention. Okay, when you attend, when the so it attends to itself. What does it mean? Suppose this FBI word is what we are focusing on. Okay, and which of the other words here attend to FBI is similar to it, somehow related to FBI. Okay, so that is the thing. Okay, you can see it as well. Okay, so you can see FBI chasing A on, these are related, more related, like that. Oh, no, no, no. So the is the word here. FBI is the word. So it attends to the here. Is it attending to FBI? I don't know what it is honestly. I mean, we'll go next into it, and the diagram is not very clear actually. Okay. So So any doubt up to this point? So we have covered autoencoders and we have understood a little bit of attention here. Okay, any doubt here? We'll go into the depth of this. Okay, nothing to worry. This is not a very important point here. So is autoencoders and PC connected? Okay, they are. PC is one solution of the autoencoder. Okay, so we'll get to that. The last slide should do it. So what they do is that so we solve PCA problem using SVD. Okay, so from SVD we know that HW star this is the structure we have here. So what you can understand, H is the so in a so H is UV U V transpose and theta, let's say. So this is the form of the SVD and H is the U here. Okay, I mean the notation is different. Okay, and so they have written like this. Okay, and so we resolve it into here. So this is the things they have done. Okay, and then resolved it into this. Okay, so this is the hmm. So the H, this is the PCA's what do you call the principal component, means the vectors. Okay, the direction of the principal component. So it stores that information. So it is given as this. Okay, and this is the autoencoder output. I think this is the input vector we have. Okay. Oh no. V is the matrix of eigenvectors of X transpose X. Okay, it is that. So it is not always the same. Okay, so as you can see, when the encoder decoder linear, inputs are normalized dimension wise, we saw that. So then this encoder and PCA becomes the same, autoencoder and PCA. But autoencoders, the importance lies in that they are non-linear. Okay, so that is why this discussion even is not so important, because they have different focus point. PC is linear, autoencoder most of the time is non-linear. Only at specific situation they become same. So just wait, let me get my computer to charge. Is it charging? No. Okay. So continuing. Okay. So further, so how to make a computer describe an image? So these two images are given. So let's get to the last of this. Very not. So this description, this captioning is required, and another dog image here. It produces another output. Okay, so it doesn't explain much here. So what they're doing, that they're handling the image through computer vision task something. They're handling the caption through a natural language processing task. Okay, that is what they explain. So this is a CNN that they have shown. This is the representation. Not much here. This is the network of recurrent neural network. Yeah. Okay. So using this, they're able to do it actually. So what they do is that they use this convolutional layer for feeding the image. Okay. Finally, some fully connected layer as well to get the smaller representation. They don't do the classification task here, so remove that. Then the feed the this is the X here, and I feed it here, so you get the output like that. Okay. And also during training, you have to also give this. Okay. What the sentence is actually. Okay. You have to do that. Okay. And then it will have learned it. Okay, and it will be able to generate. Okay, so this V is what here? Not defined V here. So whatever the output that they are getting, they are feeding it again. Okay, output then feeding it again. Okay. So we have still not gone to transformer now. This is still RNN. Okay. Some examples here. Basic. So image captioning with attention here. Okay. So what they're doing, the input image is there, convolution feature extraction using convolution network. You can get the features. Okay. And so then these features are fed to an RNN with attention. Okay. Or LSTM with attention, and then you get the result as well. So this is still not a transformer. Okay. So the process still happens sequentially. Okay. Processing is still happening sequentially. Okay. But still better, like what happens without attention, it forgets which one to attend to. Okay. But it's still not very efficient. The transformer architecture is the solution. Okay. So let me take some break. Okay. Then we'll take it up again. Okay. Good done up here now. 11. So total nine students here. Let me take a 5 minutes break. Then I will join back. Okay. So these features are fed into the network first, okay? These Z are the context vectors here, okay? Weighted features as they say. Weights are the alignment scores here, okay? And and this denotes the how the alignment scores are over the image, okay? How it this is the um, distribution over L locations as I said, the L locations here, okay? And so the distribution is, as you can see, the features are L cross D, so L rows and D columns, okay? So what they do, they use like the, so for D for a, so as you can understand, like so this is L, right? Okay, so how many D's are there? L, total L are there. Okay, so you can see each of this D1, D2, D3, like DL is like a word, okay? And so there is the attention scores on the respective words, okay? So respective columns, okay? So that is what it is. And the language part is easier, okay? So the attention over the each of the words. So using, so hard attention doesn't work too well, okay? And soft attention is usually better, okay? So image captions with attention, okay? So you can see. So now they are using LSTM, okay, in place of RNN, okay? It works better, as they say. LSTM A1. So they have shared different models, LSTM models here. Not models like strategies, training strategies. First, they have defined like A1 here. So X inverse. Let's see what is X inverse here. Huh. What is X minus to X1 and so on here? It's not very clear. They have not mentioned what is what. just get the summary. Okay. So they are first exploiting high level attributes here using this. Integrating image representations perform better. Okay, so they are is joining the representations together. So as you can see, so these are the representations. Okay, and X are the representation, I think. So they're integrating it somehow. How they're doing it? Acha, this HT. This is image patch maybe. It is given here. NS minus one. Oh. Acha, this image is this. Okay. Oh, okay. So okay, now it is understandable. So what this is, this I is the image here. Okay. So they have done TV. TV is a transformation. Acha. So okay, okay. This X are the embedding. Okay, so X minus one is the embedding when this LSTM is applied over the image, and this transformation is TV, and this is TS in the case of the sentence. Okay, so you get the embeddings like that. Okay, and next what they say, that this is the embedding, this is the embedding, and you are using a function f here, and f is what? They don't explain it much. So then you get the ht. Okay, okay, okay. So f is the RNN function. Okay, and then you get the embeddings and the hidden representation of the LSTM here. Okay, and attributes. Okay, they're also feeding the attributes here. Okay, so this is attributes here. Is it attribute? Some attribute is also given. I don't know. This is now. So from the image, this is one. This is the embedding from the attribute, and this is the embedding from the words. Okay. So they are using three things here in A2. In A3, what they are doing, captioning the attributes. Achha. These are the three things here. First, HT you get from XT, and that's it. A4, A4 they are combining this words and image together. Okay. So the image is fed to every one of the LSTM here. Okay, and this is the x minus one is the embedding of the image, which is fed at first. Okay, here, and this attribute is also fed. Okay, and that is what they've done. Now here what they do, this caption, this attributes, and these words are okay. So attribute is fed everywhere, image is only at one point. Okay, that is what it is. Okay, so let's summarize here. Benefits from mechanism: first, feeding the high level attributes into LSTM instead of starting from the image representation. So they first feed the high level attribute, then they feed the image. Okay, so integrating image representation performs better. Okay, so they're giving the high level attribute here. here what they're doing, the attributes they're feeding it to every LSTM. Okay, the noisier in image, noise is captured. Okay, so these performs better. Okay, okay, so this caption bot is the this romantic humorous. These are the uh, what do you call that, attributes. Okay, so what type of result you want, you can, you're also giving a condition or attribute into it. Okay, that is how you get it. So LSTM, what is LSTM comes? Okay, we have seen that attractive visual caption with styles. So here you can see what they're doing. So this is the our attribute, this is the caption, and this is the image. Okay, so first they are, so first with different captions they are doing. Okay, and the result you get. Okay, so the word input that they are doing, so they are usually, they're also doing a SVT style decomposition, then inputting into a LSTM. Why they are doing it is, I don't know, they have not mentioned. So style net, it does, I think, so something like that. Due to style net, they are doing the they have proposed like to do the SVT. Okay, maybe it works, I don't know. Okay, so here we are, so you're giving different what do you call it, attributes here, and accordingly you're doing some object detection here, and also generating captions. Okay, so all these things are done. Okay, okay, so we're done on this one. There's a lot of substance today actually, so it's hard to cover. Or maybe we should move to the questions now. So it is saying that you're given input data set, you don't know which type of data set, and I'm not unable to write here. I need to open it and presentation. So there is an input data set X. Can the encoder of a denoising autoencoder learn a many to one mapping from X to X? This is the question we have. Okay. So you have, so denoising autoencoder. So there is some added noise onto the. Should not able to write actually. There's some added noise onto the input X. Okay, and then it is learning mapping, many to one mapping. Okay, so what it means is that you get one output for different output. Okay, so that is correct. Okay, because we can with different noises you can generate different inputs. Okay, but the output will be the same. So the answer is A. Okay. Okay. So with regards to context vector based attention mechanisms, the context vector we've seen before transformers, so transformation came. Which of the following are likely to be true? Alignment weights can be negative, but their expected value over the distribution of the hidden states is always positive. Wrong. Alignment weights have to be positive because they are based on softmax. If the distribution in the context C vector Ct does not consider connection from k greater than t, it may not work as well as those conditions. Sure. So for connect, so k greater than t, that it is not considering. Eh, so that is correct, I think. Let me see this one. So Ct we have, if k is greater than t, okay, a specific t. So what it means is that this input is there, okay. So the h1 to hk, like that, okay. Now there is a specific t value here. Above that we don't consider for in the context vectors, okay. So then this embeddings will be this hidden representation will be invalidated in the attention scores work. So it not work so well, right? This is the answer. Such a mechanism can be made to work for spatio-temporal data such as videos. Context vector based. Yeah, this can work. Yes. B and D. Okay. Any doubt? Which of the following statements are false? No, sir. It is. Acha. Using attention-based image capturing techniques helps better explain failure cases compared to legacy techniques as the caption gets generated word by word. That's not correct actually. So attention, the thing is not generation word by word. The important thing is it is not able to forget, and it is attending to every context vector, every word hidden representation that is in the RNN or LSTM. The decoder of a visual dialogue system cannot be truly discriminating. Visual dialogue system. I don't know. Not seen this one. Blue scores are 1 and E. Transformers of parallelizable architecture in the same multiple models of the same architecture. These are the correct ones. Okay. B, C, and D. So blue scores are always between 0. Sure. Okay. Okay. Which of the following statements are true for transformer? Vision transformer do not require position encoding as they are not temporal data. This is false. It does require. Okay. We've not gone through it. Okay. But you do need the positions. Okay. To understand which embedding the image patch belongs to. Input data is parallelly passed to all stacked encoders in a transformer. Yes. Acha, acha. So what the thing is that so it is passed one after another actually. So both of these are wrong actually. The answer is C. Acha. Acha. This thing is there. Okay. Now, so standard attention mechanism. This is what the softmax attention does. Okay. So all entries in Q, K, Q, V, right? So multiplied by scalar X, all of those in Y, K with Y, denoted by the event. Acha, acha, that's what they've done. So this is how to do it actually. If X multiplied Y, the multiplication that you're doing is greater than 1, then it goes down. Otherwise, if it is equal to, then it stays the same, else it goes up. Okay. Now, so this is the uh, qu- this is the sinusoidal position encodings. Okay. So there you have to equate this these two. Okay. And you get the answer. Okay. So that's how it is. Okay. Okay, we'll finish off here. Okay. Anybody's in doubt? Okay.